Hi everyone, today we'll be looking at the January 2020 Mechanics 1 paper. In question 1, we've got two particles P and Q of mass M1 and M2 respectively. They are moving on a smooth horizontal plane and they are moving towards each other in opposite directions along the same straight line when they collide directly. So this is P, this is Q. We've got M1 and M2, the masses. Now, immediately before the collision, both particles are moving with speed u. So I like to write it before here. So before, they are moving towards each other with speeds of u. So this is u, and this is also u. And then after the collision, the direction of motion is reversed and the speed of q is a third u. So we know that q is moving to the right with a speed of a third u. So there it is. And p is moving to the left with the speed of v. We need to find in terms of m2 and u the magnitude of the impulse exerted by P on Q in the collision. We know that the impulse is the change in momentum. So we need to consider how the momentum changed during the impulse. So we will be considering Q in order to obtain an expression in terms of M2 and U. The momentum after is m2 times a third u. I'm taking the direction to the right to be the positive direction here, obviously, minus the momentum before, which is m2 times the negative u, because it's in the opposite direction. So this is a third m2u plus m2u, which gives an answer of 4/3 m2u Newton seconds. In B, we need to find in terms of m1, m2, and the u, the speed of P immediately after the collision. So I'm going to be considering conservation of momentum, whereby the total momentum before is equal to the total momentum after the collision, and therefore this means that m1u plus m2 times negative u, this is the momentum before, is equal to m1 times negative v plus m2 times a third u. So we've got m1u minus m2u is minus m1v plus a third m2u. We need to solve for v, so m1v is equal to 4/3 m2u minus m1u, and this leads to v being 4/3 m2u minus m1u, and all of it over m1. That's an expression for v. This can be further simplified into 4/3 m2 minus m1. I'm factoring out the u over m1. In C, it says, hence show that m2 is greater than 3/4 m1. So from the expression we obtained for v, for the speed, we know that v must be positive. So we know that v is greater than 0, which means that 4/3 m2 minus m1 u over m1 is greater than 0. Now u and m1 are both positive quantities, so this means that we also need 4/3 m2 minus m1 to be greater than 0. So 4 over 3 m2 is greater than m1, which leads to m2 being greater than 3 over 4 m1 as required. Question 2, we've got a non-uniform beam AB with a length of 6 meters, weight of W newtons. It's being supported in equilibrium in a horizontal position by 2 vertical ropes, one attached to the beam at A and the other to the beam at C. CB is 1.5 meters. The center of the mass is 2.625 meters from A. So I could start by adding some forces here. This is the weight here. The distance is 2.625 meters. Now this is obviously 4.5 meters. Now the ropes are modeled as light strings. The beam is modeled as a non-uniform rod. The tension in the rope at C is 20 newtons, greater than the tension at A. So if I call this tension here T, then the tension here will be T plus 20. So I've got all the forces here. We need to find the value of W. So in order to do that, I will be taking moments about A. So if we think about it, the clockwise moment is 2.625 times W, and the anti-clockwise moment is 4.5 times T plus 20. If I expand this, I get 2.625 W is 4.5 T plus 90. In addition, the total upward forces is equal to the total downward forces because this is in equilibrium, and therefore we've got that T plus 20 is equal to W, which means that 2T is W minus 20, and therefore T is W minus 20 over 2. And I will actually be solving this as a system of simultaneous linear equations. So we end up with 2.625 W being 4.5 brackets W minus 20 over 2 plus 90. So if we expand, we get 2.625 W is equal to 2.25 W minus 45 plus 90, which means that 0.375 W is equal to 45, and therefore W is 120 newtons. Part B, state how you have used the fact that the beam is modeled as a rod. Well, we have assumed that the beam will not bend, so that's the assumption behind modeling something as a rod. It will not bend under the action of the different forces, so assumed the beam will not bend. In question 3, we've got a particle P which is projected vertically upwards with a speed of u from a fixed point O. At the instant when P reaches its greatest height, h above O, we've got a second particle Q which is projected with speed a half u vertically upwards from O. We need to find h in terms of u and g, and then we need to find the time between the instant when Q is projected and the instant when the two particles collide. Obviously, I need to start by investing some time drawing a nice diagram illustrating all the given information just to have a visual understanding of what's happening. This is the situation here. We've got P projected from ground with an upward speed of u. It reaches a maximum height of h, then goes down. The moment that P attains the maximum height h, Q is projected upwards with a speed of a half u. At some point they collide. at this point that they have the same height and it's the same time. So let's start by finding h in terms of u and g. So I will start by considering p. I'll be using v squared is u squared plus 2as, because we know that when the maximum height is attained, the speed is 0. The original speed is u. The acceleration is minus g because gravity is opposing motion, and the height attained, the s, is capital H. So 2gh is u squared, and therefore h is u squared over 2g meters. In B, we need to find the time between the instant when Q is projected and the instant when the two particles collide. I could actually concentrate from the moment that P reaches the maximum and starts its descent, because this is exactly the moment that Q is projected, so the time is compatible. So if I consider P again and use that S is ut plus a half at squared, I can say that the displacement of P from its maximum is 0t plus a half gt squared, because I'm modeling this motion here, a starting initial velocity of 0, it's going down, so the acceleration is g, and therefore we've got that sp, the displacement of p, is simply a half gt squared. Similarly, if I was to consider q, we've got that the displacement of q from its original launching point is a half ut plus a half minus gt squared. So this is just a half ut minus a half gt squared. So looking at the diagram, SP is this distance here. I might as well note this. This is SP, the distance that P has covered, and this is SQ. And it's obvious that the two added up should give me H. So SP plus SQ is H, and I'll be substituting a half GT squared plus a half ut minus a half gt squared is equal to u squared over 2g. Now the gt squared terms cancel out, the 2 with the 2 cancels out, the u with the u squared, and I'm left with t is u over g seconds. I was asked to find the time here in terms of u and g. And then part C, find where the two particles collide. So I could start by finding SQ, now that I've got an expression for t, and then say it's so many meters above the launching point, above the origin. So I'm just gonna say that when t is equal to u over g, as we have just established in part B, then the displacement of q is a half u over g, I'm replacing t with u over g, minus a half g u over g all squared. This is u squared over 2g minus, we've got u squared, the g with the g squared will leave me a g in the denominator, so 2g. So this is just 0. It means that they will collide 0 meters above the launching point of Q, so essentially they will collide at O. So if we go back to the question itself for a moment, the wording used find where the two particles will collide, not find the distance or the height above O, was hinting at a kind of an answer that we got at the end. So the two particles will collide on the ground at O. In question 4, we've got two identical small rings, A and B, each of mass M, threaded onto a rough horizontal wire. The rings are connected by a light and extensible string. This is the string here. A particle C of mass 3m is attached to the midpoint of the string. It hangs in equilibrium below the wire with an angle of BAC being β, as shown in the figure. The tension is T, and by considering the particle C, we need to find capital T in terms of M, G, and β. I could start by adding the forces that act on C. I have added the tensions here. I have added the weight for C. So it's easy to see that the upward force here would be T sine β times 2. So overall here, this force will be 2 times T sine β, and therefore, because this is in equilibrium, I will just equate the upward forces with the downward forces and say that 2T sine β is equal to 3mg, which leads to T being 3mg over 2 sine β. In B, we need to find, in terms of M and G, the magnitude of the normal reaction between the wire and A. So that what I will do now is that I will be adding the forces that act on A in order to see exactly what's happening and ending up with an expression for the reaction here. So if you think about it, now that we've got the forces here, A is feeling its weight, it's feeling the tension here, and it's feeling a reaction that's pointing upwards. So the component of T that's acting downwards is T sine β. So the overall downward force will be T sine β plus mg. So I'm just gonna say that T sine β plus mg is equal to R. We know that T is 3mg over 2 sine β, so 3mg over 2 sine β times sine β plus mg is equal to R. The sine β's cancel out, and 3 over 2mg plus 1mg is 5 over 2mg. And this is the reaction between the wire and A. Now the coefficient of friction between each ring and the wire is 4 over 5, and the two rings A and B are on the point of sliding along the wire towards each other. I need to find the value of tan β. So I need to add the horizontal forces that act on A, and this will help me find the value of tan β. So to the right, I've got a component of T cos β. So I'm just gonna put it here. And they are on a point of sliding towards each other, so A is gonna go to the right. So we've got a frictional force to the left, which is equal to mu R. So based on this, we know that mu R is T cos β. And I'm gonna be replacing R with the value we just found. We know that mu is 4 over 5. R is 5 over 2mg. T is 3mg over 2 sine beta, and cos beta is there. We've got some simplifications. The 4 with the 2 leaves me a 2, the 5 with the 5, the mg with the mg. So all in all, I'm left with 4 sine beta is 3 cos beta. I will be dividing both sides by 3 cos beta. So I get 4 over 3 tan beta equals to 1, or simply that tan beta is 3 over 4. In question 5, we've got a car traveling at a constant speed of 40 meters per second in a straight line. At t0, it passes a motorcyclist who is at rest. The motorcyclist immediately sets off and accelerates at 4 meters per square second for 15 seconds, and then accelerates at 1 meter per square second for the further capital T seconds until they catch up with the car. Now we need to sketch on the same axis the speed time graph for the motion of the car and the speed time graph for the motion of the motorcyclist. Now we know that in a speed time graph, it's the gradient that gives me the acceleration. So this is what the graph looks like. I have to explain a few things. First of all, the car, it's traveling at a constant speed of 40 meters per second. So it's a horizontal line, there it is. Now the motorcyclist, they set off from rest. They accelerate at 4 meters per square second for 15 seconds, there it is. So if I just use rise over run, I see that this must be 60, because 60 over 15 is equal to 4. And then we've got an acceleration of 1 meter per square second, so certainly less steep of a line here for the next capital T seconds. So this was 15 seconds, so this is 15 plus capital T. Now, over this capital T seconds, the gradient was 1, so the rise should be capital T, and therefore the speed goes from 60 to 60 plus capital T. Notice that I cannot use any Suvat equations here because we've got different acceleration for the first 15 seconds and a different acceleration for the remaining of the journey. Now, at the instant when t is t1 seconds, the car and the motorcyclist are moving at the same speed. So this is t1 here, the speeds match. So I'll be using exactly the same idea. Rise over run is equal to gradient. Now the rise is 40, the run is t1, and the gradient is 4. So 40 over 4 is t1. So 10 seconds is the time we had to find. 10 seconds. And then C, show that capital T squared plus K capital T minus 300 is 0, where K is a constant to be found. Well, because we were told that they catch up, the motorcyclist catches up with the car, it means that the area under the speed time graph, which is the distance, should be the same. So the area for the car and then the area for the motorcycle should be the same. So for the car, it's easy. It's a rectangle of a width of 15 plus t and a height of 40. And for the motorcycle, I could treat it as a triangle and then a trapezium. A trapezium having base 1 of 60, base 2 of 60 plus capital T, and a height of capital T. So let's put everything together here. We've got that 40 times 15 plus capital T is equal to 15 times 60 over 2. This is the triangle I was mentioning, plus the trapezium, which is base 1 plus base 2 over 2 times the height of T. So we get 600 plus 40 T is equal to 450 plus 120 plus T over 2 times T. I will multiply everything by 2 to get rid of the fractions. So 1200 plus 80T is 900 plus 120T plus T squared. So 0 is T squared plus 40T minus 300, and therefore the constant K is 40. In question 6, we've got a force F, it's 10I plus J newtons. We need to find the exact value of the magnitude of F. We know that the magnitude is given essentially by Pythagoras, and it's just 10 squared plus 1 squared square root. So we need the exact value, no calculator here, it's root of 101 newtons. Now in B, we need to find in degrees the size of the angle between the direction of F and the direction of the vector I plus J. Now it certainly makes sense to quickly draw a diagram to illustrate what's happening here, and this is what we have. This is the force F. It's going 10 to the right, 1 up. I'm calling this angle here phi. And then we've got the other vector here, which goes 1 to the right and 1 up. It's obviously an isosceles right angle triangle, so this angle here is 45 degrees. We want to find the angle between the two vectors, so we want to find theta here, which is just going to be 45 minus phi. So tan phi is 1 over 10, which gives me phi to be 5.711, and then theta is just 45 minus 5.711, which is equal to 39.3 degrees. In C, we're being told that the resultant of F and this force here, A is a constant, is parallel to but in opposite direction to the vector 2I minus 3J. We need to find the value of A. First of all, the resultant means the sum of the forces. So if I add up F and this force of minus 15I plus AJ, this is parallel but in opposite direction to 2 minus 3. Now parallel means a multiple, and if it's in the opposite direction, I'm just gonna switch the signs around, so that will become negative and that will become positive. So it's gonna be equal to lambda times minus 2, 3. So F was 10, 1 plus negative 15A is equal to minus 2 lambda, 3 lambda. If I equate the I components, 10 plus minus 15 is minus 2 lambda. So 10 minus 15 is 2 lambda, which leads to, minus 2 lambda, which leads to minus 5 is minus 2 lambda. So 5 over 2 is the value of lambda. And if I equate the J components, I get that 1 plus A is 3 lambda. So 1 plus A is 3 times 5 over 2. 1 plus A is 15 over 2. And therefore we get that A is 13 over 2. In question 7, we've got the particle A of mass 4 kilograms being held at rest on a rough horizontal table. It's attached to one end of a string passing over the pulley here P. The pulley is smooth. It is fixed at the edge of the table. The other end is attached to a particle B of mass 3 kilograms hanging freely below P. Now we're modeling the string as being light and extensible, the pulley as being small, smooth and light. We release the system from rest, and at the instant of release, A is 2 meters from the edge of the table and B is 1.4 meters above horizontal floor. After descending with a constant acceleration for 2 seconds, B hits the floor and does not rebound. We need to show that the acceleration of A before B hits the floor is 0.7 meters per square second. First of all, the fact that the string is inextensible means that both B and A experience the same acceleration. I will start by considering B. We know that B is released from rest, so the initial velocity is 0. We know that the displacement, the distance covered, is 1.4 meters because that's the distance to hit the ground, and the journey took 2 seconds. So in order for me to find the acceleration, I can use S is ut plus a half at squared. So 1.4 is 0 plus a half times A times 2 squared. 1.4 is 2A, leading to 0.7 meters per square second, being A as required. In B, we need to state which of the modeling assumptions we have used in order to answer part A, and obviously it's the fact that the string is inextensible, and that's the reason that both particles have the same acceleration. In C, we need to find the magnitude of the resultant force exerted on the pulley by the string. Now that I have to consider forces, I think it makes sense to go to my diagram and actually add all the forces that are acting here. So this is the situation here. We've got B feeling its weight, 3g newtons. There's a tension pointing upwards, and then for particle A, it's the weight. For G, it's the reaction, equal and in the opposite direction. We've got tension to the right, and we've got a frictional force to the left, which is obviously mu times the normal force R. They are both experiencing the same acceleration, which we have found to be 0.7 meters per square second. Now we need to find the magnitude of the resultant force exerted on the pulley by the string. I will start by finding the tension, and this will happen by considering B here. So considering B is moving downwards, so downward forces minus upward forces is mass times acceleration. This leads to 3g minus t is 2.1, so 3 times 9.8 minus 2.1 is t, which gives me that t is 27.3 newtons. Now that we've got the tension, let's go back to the diagram. Let's look at the pulley. If we consider what the pulley is feeling, this is exactly what's happening here. The pulley is feeling a tension pointing downwards and an equal magnitude tension to the left. So I could enlarge this here, and it would look something like this. This is an isosceles triangle of sides T and T, and the resultant is the diagonal here, what I have called F, which by Pythagoras theorem is simply being given by t squared plus t squared and all square root. So once more, P is feeling being pulled to the left and being pulled downwards with an equal sized force of T. So now that we've got the value of T, I'm just gonna say that the force I'm trying to find, F, is 27.3 squared plus 27.3 squared, all square root, which gives me an answer of 38.6 newtons. Now, in D, we need to find the value of the coefficient of friction between A and the table. So looking at the forces acting on A, So I will be considering A. We can write down that A is moving to the right, so forces acting to the right, T, minus forces acting to the left, that's the resultant, is mass times acceleration. T has been found to be 27.3. Mu is what we're trying to find. The R is the weight, the 4G, and this is 4 times 0.7. So 27.3 minus 4 mu G is 2.8, which means that 27.3 minus 2.8 is 4 mu G. So 27.3 minus 2.8 over 4G is mu. If I plug this on the calculator, I get an answer of 5/8. However, you need to give it as a decimal to 2 or 3 SF. Do not give the exact value of 5/8 because this depends on the value of G that you have used. We have used 9.8. If someone would use maybe 10 or 9.81, they will be getting a different answer. So we are not justifying in giving an exact answer. We go to 2 or 3 SF. E, determined by calculation whether or not A will reach the pulley. Well, if we think of the situation, B will descend by 1.4 meters, which means that A will move to the right by 1.4 meters. It will have another 0.6 meters until hitting the pulley. The question is, will it cover this distance before it stops? Now, the moment that B hits the floor, the string goes slack and there is no longer tension in the string. The only force acting will be the frictional force here, so A will start decelerating, eventually coming to a stop. We need to determine the distance covered while decelerating. So we know that A covers 1.4 meters until B hits the floor. And at that point, it is 0.6 meters from the pulley. I will start by finding the speed with which B hits the floor. I'll be using V equals U plus AT. So V is 0 plus 0.7 times 2. V is 1.4 meters per second. This is the speed with which B hits the floor, and it's the initial speed, the starting speed for A when it starts the journey over which the string goes slack. So if I consider considering A, I will now consider A to find the acceleration over the journey that the string is slack. So considering A is still moving to the right, so forces to the right, which is 0, minus forces to the left, which is mu r, is mass times acceleration. So minus 0.625 times 4g is 4a. The force cancel out, and I'm left with minus 0.625g being the acceleration. It turned out to be negative, obviously, because it's decelerating. So I've got the acceleration, I've got the initial speed. When it comes to rest, it's going to be 0 meters per second. So I'll be using v squared is u squared plus 2as. So 0 squared is 1.4 squared plus 2 times minus 0.625g times S. So this leads to 0 is 1.96 minus 1.25 GS. So I'm solving for S. The big question is what value will S give me and whether this will be greater than or less than the 0.6. It turns out to be 0.16. In other words, this is less than the 0.6 meters that was the distance to the pulley. So this is less than 0.6 meters and therefore it will not reach the pulley.